Good afternoon. My name is Clevis Aliyah, and I'm a PhD student at the University of Utah in the Bioengineering Department. Today, I will share with you the results of a numerical investigation of the flow around a Lily Impeller at two different Reynolds numbers, 12 and 60. We use the standard Reynolds number equation to calculate the Reynolds number and chose the length of the Lily to be the characteristic length scale, which is 0.04195 meters, because it is in the direction of the flow. A simulation domain conforms to measurements of the water channel that is used for validation of our simulation. It has a length of 0.61 meters and a frontal area of 0.15 meters squared. The water lily itself has dimensions of 0.04195 meters for length and 0.0343 meters for height. We chose an external flow simulation in SolidWorks and modeled the walls of the lily with 50 micrometer roughness. And our ambient velocity in the simulation was set to 0.58735 meters per second for the Reynolds number of 12 and 2.9367 meters per second for the Reynolds number of 60. Our numerical results compare favorably to our experimental results, especially given the fact that our water channel experiment had many sources of error. The encouraging trend is that with increasing Reynolds number, the percentage difference between the numerical results and the experimental results decreases. We will now look at the Lily Impeller in our water channel experiment with a Reynolds number of 8. Notice the backflow right behind the Lily Impeller. We'll now look at the Lily Impeller in the water channel experiment with a Reynolds number of 12. Notice the backflow behind the Lily Impeller, but also notice that it is much less than the Reynolds number of 8 water channel experiment. We will now look at the Lily Impeller with a numerical simulation with a Reynolds number of 12. Again, note the backflow behind the Lily Impeller. We will now look at the Lily Impeller in a numerical simulation with a Reynolds number of 60. Note that there is much less backflow as compared to the numerical simulation with a Reynolds number of 12. The vorticity isolines show us that in the experiment with a Reynolds number of 12, there exists vorticity gradients behind the water lily as compared to the Reynolds number of 60 experiment. The vorticity gradients could be causing the backflow in the lower Reynolds number experiments. We also note that, as expected, there is a higher pressure gradient between the front and the back of the water lily in the higher Reynolds number experiments as compared to the lower Reynolds number experiments. In conclusion, we validated our numerical model against water channel experimental data. Both in the experimental data and in the numerical model, we note that at lower Reynolds number, there is backflow behind the Lily Impeller. We theorize that the vorticity gradients behind the Lily Impeller lead to this backflow in the lower Reynolds number experiments.